Have you ever looked up at the night sky and wondered if we are truly alone? The vastness of the cosmos stretches beyond comprehension, with billions of stars, countless planets, and mysteries we have only begun to unravel. What if I told you that the very origins of life on our planet might not be as homegrown as we once believed? What if the building blocks of existence, the spark that ignited life billions of years ago, didn't begin here on Earth at all? This isn't science fiction. It's a compelling scientific idea that challenges everything we think we know about where we come from, and it's known as the panspermia hypothesis. Imagine for a moment that life is a cosmic traveler. Picture microscopic organisms, hardy and resilient, hitching a ride on asteroids, meteoroids, and comets, journeying across the immense distances of space. These celestial voyagers survive the harsh vacuum, extreme temperatures, and radiation, eventually reaching new worlds, including our own. When they arrive, they bring with them the potential for life, seeding planets with biological material that blossoms into the diversity we see today. This idea suggests that life is not unique to Earth but is a fundamental part of the universe, scattered like stardust across the galaxies, just waiting for the right conditions to take root. In this video, we're going to explore this extraordinary possibility. We'll dive into the science behind the panspermia hypothesis, examining the evidence that supports it and the questions that still remain. From the depths of space to the earliest moments of life on our planet, we'll journey together to understand whether humanity itself might have extraterrestrial origins. This is more than just a theory, it's a paradigm shift that redefines our place in the cosmos. So join me as we venture into one of the most profound and awe-inspiring ideas science has to offer, and discover what it could mean for the future of life, both here on Earth and beyond. The very word panspermia offers a clue to its grand, poetic scale. It comes from the ancient Greek words pan, meaning all, and sperma, meaning seed. So, literally, it translates to seeds everywhere, painting a picture of a universe teeming with the potential for life, just waiting for the right conditions to sprout. This idea fundamentally repositions our planet from a solitary cradle of life to a potential recipient in a much larger cosmic ecosystem. For centuries, the prevailing scientific mystery has been abiogenesis, the process by which life arose naturally from non-living matter on the early Earth. This is a complex puzzle involving countless chemical reactions happening in just the right sequence under precisely the right conditions. One of the most significant challenges for Earth-bound abiogenesis is the surprisingly short window of time it had to occur. Geological evidence tells us that Earth formed about 4.5 billion years ago, and it spent its first several hundred million years as a molten, hostile world, constantly bombarded by asteroids during a period called the Late Heavy Bombardment. Yet, we have fossilized evidence of microbial life that is at least 3.5 billion years old. This means that life emerged and established itself on our planet in a relatively narrow geologic instant, perhaps as little as 200 million years, once the environment became even remotely stable. For some scientists, this timeline feels incredibly tight, almost too fast for all the necessary chemical precursors to have assembled by chance in Earth's primordial soup. The panspermia hypothesis offers an elegant, though still speculative, solution to this timing problem. It suggests that life did not have to start from absolute scratch here. Instead, the most difficult part, the formation of those initial, self-replicating biological molecules, could have occurred somewhere else in the cosmos, on a planet that formed billions of years before Earth even existed. This process would have had a much longer head start. Then, through the incredible journeys of asteroids and comets, those pre-formed seeds of life could have been delivered to a freshly cooled Earth, effectively jump-starting the biosphere the moment our planet was ready. It doesn't necessarily make the origin of life itself any less miraculous, but it does relocate that miracle from our specific planet to the universe at large, potentially making life an inevitable and widespread phenomenon rather than a single freak accident on one world. While the idea might seem like a product of modern astrobiology, its roots stretch back millennia, deeply embedded in human philosophy. The first inklings of this concept can be traced to the brilliant and often controversial mind of the Greek philosopher Anaxagoras in the 5th century BC. Living in a time when science and philosophy were one and the same, Anaxagoras looked at the universe and proposed that all things, including life itself, were composed of tiny, fundamental seeds. He called these primordial particles spermata, and he theorized that they were present throughout the cosmos, suggesting that the building blocks of life were universal and not confined to our world. His was a visionary idea born not of telescopes and microscopes, but of pure logical deduction about the nature of existence. For this radical thinking, which challenged the earthly-centric views of his time, he was ultimately tried for impiety and exiled from Athens. His concept of cosmic seeds, however, refused to die. The idea lay dormant for centuries, a speculative footnote in the history of philosophy, until the dawn of modern science provided new tools and a new context for it to flourish. In the 19th century, other scientists like Lord Kelvin and Hermann von Helmholtz began to seriously reconsider the notion, pondering if meteorites could have ferried life to our planet. But it was the Swedish Nobel Prize-winning chemist Svante Arrhenius who, in the early 20th century, gave the hypothesis its first truly scientific formulation and its famous name, panspermia. Arrhenius took the ancient idea and clothed it in the physics of his day. He proposed that microscopic, dormant spores, perhaps encased in protective material, could indeed journey between planets. But his proposed engine for this incredible voyage was not impact events, it was light itself. Arrhenius theorized that the tiny but constant pressure of radiation from stars could literally push these microscopic life seeds through the vacuum of space. He calculated that over immense periods, these particles could be propelled from one star system to another, sailing on sunbeams across the galaxy. This concept, which he called radiopanspermia, captured the scientific imagination of the era. It was elegant, poetic, and grounded in known physics. However, this early model soon encountered significant hurdles. As our understanding of space deepened, scientists realized the environment was far more hostile than Arrhenius had known. The intense cold, vacuum desiccation, and most critically, the relentless and deadly barrage of cosmic and stellar radiation would likely shatter the complex molecules of life and sterilize any unprotected spore on such a long journey. While his specific mechanism fell out of favor, Arrhenius's greatest contribution was monumental. He successfully moved the conversation from the realm of pure philosophy into the arena of empirical science, setting the stage for a century of debate and discovery. So if radiation pressure wasn't a viable engine for life's journey, what mechanism could possibly protect these delicate biological passengers on a violent trip across the solar system? This brings us to the most compelling and widely studied version of the hypothesis, known as lithopanspermia, literally rock seeds. This modern theory provides a far more robust and physically plausible scenario for how life might actually hitch a ride between worlds. Instead of fragile spores drifting naked through the void, lithopanspermia envisions microorganisms as ultimate stowaways, traveling safely nestled within the protective confines of rocks. The entire incredible process begins with a cataclysmic event, a massive asteroid or comet slamming into a life-bearing planet. The force of such an impact is almost unimaginable, generating temperatures hotter than the surface of the sun and pressures immense enough to instantly vaporize rock. It seems counterintuitive that anything could survive this inferno, but planetary scientists have calculated that not all material from the impact is subjected to the most extreme conditions. Rocks near the surface, away from the direct point of impact, can be blasted off into space without being completely melted or vaporized. These ejected fragments, now known as meteoroids, become lifeboats for any hardy microbes living deep within their tiny pores and fissures. For a microbe living inside a rock, the experience of being ejected from a planet would be utterly violent, subjecting it to extreme G-forces. Yet, experiments here on Earth have shown that certain types of bacteria, known as extremophiles, can survive accelerations thousands of times greater than Earth's gravity. Once freed from its planet's gravity, this rocky vessel and its microbial cargo embark on an epic journey through interplanetary space. This is where the real protection of the rock becomes essential. The interior of a decent-sized meteoroid acts as a fantastic shield, buffering its passengers from the most deadly hazards of space. It provides protection from the extreme temperature fluctuations between sunlight and shadow. It offers a barrier against the relentless DNA-shredding power of cosmic radiation, which would quickly sterilize any exposed organism. Perhaps most importantly, the rock seals the microbes inside, preventing them from completely drying out in the vacuum of space and preserving them in a state of suspended animation. This journey isn't a quick one. It could last for millions of years as the rock tumbles through the solar system, its trajectory dictated by gravity. Eventually, through sheer chance, its path might intersect with another planet. The final fiery hurdle is atmospheric entry. We've all seen shooting stars, the bright streak of a meteor burning up in the atmosphere. It seems like certain doom for any biological material. However, a sufficiently large rock can actually survive this process. While the exterior of the meteoroid ablates away, burning up and creating that brilliant glow, the interior can remain relatively cool, acting as a heat shield for the microbes tucked deep inside. We have physical proof that this is possible because we find these survivors on Earth all the time. They're called meteorites. Studies have shown that the core of a meteorite often remains completely unaltered during its passage through the atmosphere, never reaching temperatures that would kill all known forms of life. If that meteorite then crashes into a welcoming new world, a planet with liquid water and a suitable atmosphere, the final act of this billion-to-one journey can unfold. The rock fractures on impact, releasing its microbial passengers into a new environment where they can potentially awaken, multiply, and begin seeding a whole new world with life. This isn't just a theoretical story, it's a chain of events, each step of which is supported by experimental evidence and our understanding of physics, making pseudo-panspermia a profoundly compelling idea for how life could spread. While the protective embrace of a rock offers a compelling ride, another proposed method for life's journey is far more elegant and direct, yet also faces far greater challenges. This is the concept of radiation panspermia, the original idea put forth by Svante Arrhenius. Imagine, if you will, a single microscopic spore, perhaps no larger than a speck of dust. Instead of being buried safely inside an asteroid, this tiny organism is floating freely in the void, and it's moving not by the chaotic force of an impact, but by the gentle, persistent push of starlight itself. This is the principle of radiation pressure. Photons, the particles of light that stream constantly from stars, carry a tiny amount of momentum. When they strike an object, they impart a minuscule push. For something as large as a person or a spaceship, this force is completely negligible. But for a particle as small as a bacterium or a spore, this constant pressure can, over immense timescales, act like a steady solar wind, accelerating it to tremendous speeds and potentially propelling it from one star system to another. It's a beautifully simple and poetic idea, life sailing on sunbeams across the galaxy. The feasibility of this method, however, quickly runs into the harsh realities of the interstellar environment. The first and most immediate challenge is the sheer destructiveness of the very radiation meant to propel the spore. Cosmic radiation and ultraviolet light from stars are incredibly effective at breaking apart the complex organic molecules that constitute life, such as DNA and proteins. Without the several inches of solid rock shielding provided by lithopanspermia, a spore drifting in space would be completely exposed to this relentless barrage. Even if the organism were in a dormant state, its genetic material would be shredded by high-energy particles long before it could travel any meaningful distance. Then there is the issue of the vacuum of space itself. Without pressure, water instantly sublimes, turning directly from ice into vapor. This would cause catastrophic desiccation, ripping the water molecules right out of the cell and effectively mummifying it. Furthermore, the extreme cold of space, hovering just a few degrees above absolute zero, would pose another barrier, potentially damaging cellular structures through the formation of ice crystals if any water somehow remained. Perhaps the most daunting challenge is the immense timescale required for interstellar travel. Even traveling at a significant fraction of the speed of light, a journey to the nearest star system, Proxima Centauri, would take thousands of years. A spore moving under radiation pressure would be far slower, making its journey an epic voyage lasting not thousands, but millions or even tens of millions of years. Surviving the relentless radiation and deep freeze for such an astronomical period stretches the limits of what we believe is biologically possible. While we have discovered remarkable extremophiles on Earth that can survive in a dormant state for millions of years encased in salt or permafrost, these are still protected environments, not the completely exposed and utterly hostile conditions of interstellar space. For these reasons, radiation panspermia is generally considered far less plausible than its rocky counterpart. Yet, it remains a fascinating cornerstone in the history of this idea, a testament to the human desire to find elegant, universal solutions to life's biggest questions, and a reminder that sometimes the most beautiful theories must yield to the uncompromising laws of physics. But what if the journey of life wasn't just a matter of random cosmic chance, a fortunate accident of physics and biology? What if instead it was a deliberate act? This brings us to one of the most provocative and mind-bending variations of the hypothesis, known as directed panspermia. This theory proposes that the seeds of life on Earth were not delivered by a blind, natural process, but were intentionally sent here by an advanced extraterrestrial civilization. It's the idea that we might be part of a grand, galactic-scale gardening project. This concept was first formally proposed in the 1970s by none other than Francis Crick, the Nobel Prize-winning co-discoverer of the structure of DNA, along with his colleague, the renowned chemist Leslie Orgel. These were not fringe scientists, they were giants in their field wrestling with a fundamental problem. Crick and Orgel found the sudden, rapid emergence of life on a freshly formed Earth to be, statistically, incredibly improbable. As a solution, they seriously entertained the idea that the blueprint for life, perhaps in the form of resilient microorganisms or even encoded genetic material, could have been purposely dispatched to our planet by intelligent beings from another world. They suggested that an advanced civilization, facing its own impending doom or simply seeking to propagate life, might load primitive organisms into a sturdy, robotic spacecraft and aim it at promising, habitable planets they had identified across the galaxy. The implications of this idea are staggering, touching on both science and philosophy. From a scientific standpoint, it offers a neat, albeit extraordinary, solution to the timing problem of life's origin. It effectively outsources the most difficult part of the equation, the initial genesis of a self-replicating system, to another place and time, one that had a much longer head start on universal evolution. Philosophically, it completely upends our place in the cosmos. It transforms humanity from a potential miracle of isolated evolution into a possible biological experiment, or perhaps even a form of cosmic heritage. It raises profound and somewhat unsettling questions. If this is true, are we the intended product or an accidental byproduct? Are we alone in the universe, or are we, in a very literal sense, related to our celestial neighbors? The concept of directed panspermia blurs the line between science and science fiction, and Crick and Orgel themselves were fully aware of its speculative nature. They presented it not as a proven fact, but as a serious scientific hypothesis that was, at the very least, worth considering and one that should be capable of being tested. For instance, if life was designed to be seeded, we might find a universal biological signature in our genetic code, an unmistakable pattern that defies natural explanation. While the evidence for such a directed mission remains entirely elusive, the theory forces us to confront the limits of our current understanding and to boldly consider possibilities that challenge the very foundation of what we believe about our own existence. It expands the narrative of panspermia from a story of random celestial billiards to one of potential purpose and intention on an unimaginable scale. Now, let's turn our gaze to our closest planetary neighbor, a world that has captivated scientists and storytellers for generations, Mars. This isn't just about little green men. The red planet presents one of the most tangible and scientifically compelling scenarios for panspermia. The idea isn't that Martians invaded, but that we might, in fact, be Martians ourselves. This possibility hinges on a fascinating reversal of planetary fortunes and a period of cosmic violence that connected our two worlds. Billions of years ago, the conditions on Mars and Earth were dramatically different from what we see today. While the early Earth was still a molten hellscape cooling from its violent formation, Mars was quietly getting a head start. Because it is a smaller planet, it cooled down much more rapidly. Evidence gathered from orbiters and rovers on its surface paints a picture of a surprisingly inviting ancient Mars. It had a thicker atmosphere that provided warmth and shielding from radiation. Most importantly, it had vast quantities of liquid water flowing across its surface. We see the unmistakable scars of dried-up riverbeds, deltas, and the basins of ancient lakes and even oceans. This means that at a time when Earth was still largely uninhabitable, Mars was a stable, wet, and potentially habitable world. It had a significant jump start, perhaps as long as 500 million years, to cook up the chemistry of life in its tranquil waters. If the basic ingredients for life are a universal outcome of planetary chemistry, then Mars had a much longer, quieter, and more favorable window to get the process started. This sets the stage for the second crucial part of the Martian connection, the Great Celestial Shipping Network. During the early solar system, a period known as the Late Heavy Bombardment, both Earth and Mars were under constant assault by a rain of asteroids and comets. These impacts were so powerful that they could blast enormous chunks of a planet's crust clear out of its gravitational pull. Crucially, because Mars has much weaker gravity than Earth, it is far easier to launch material from its surface into space. Computer models show that a significant number of these Martian rocks, containing potential microbial stowaways, would have been flung on trajectories that eventually crossed paths with Earth. We know this exchange happened because we have physical proof right here on Earth. We have discovered meteorites that we have definitively identified as coming from Mars. These rocks were blasted off the Martian surface by ancient impacts. They journeyed through space for millions of years, and they eventually fell to Earth. If rocks can make the trip, then anything living inside them could have too. The journey from Mars to Earth is also, astronomically speaking, relatively short. While a trip between star systems takes millions of years, a transfer from Mars to Earth might only take a few months to a few years. This drastically reduces the survival time for any microorganisms, making the entire proposition far more plausible than an interstellar voyage. They would have less exposure to cosmic radiation and the other deadly hazards of space. When we consider that we have extremophile bacteria on Earth that can easily survive in a dormant state for such timeframes, the idea moves from the realm of pure speculation into a legitimate, testable scientific pathway. The theory suggests that after enduring its early bombardment, a now habitable Earth was continually seeded by rocks arriving from a dying Mars. As the red planet lost its atmosphere and its water dried up, its biological legacy, if it had one, may have found a new, vibrant home next door, eventually evolving into every living thing we see around us today. This doesn't diminish the miracle of life on Earth. It simply suggests that our most profound origin story might have begun on the rust-colored plains of another world entirely. This incredible journey from the surface of Mars to the deserts of Earth is only possible because of a very special kind of passenger. The rocks are just the vehicles, the true pioneers are the organisms hitching a ride inside. For panspermia to be more than a theoretical possibility, we need to find life forms capable of surviving every brutal stage of that trip. The violent ejection, the cold vacuum of space, the relentless radiation, and the fiery re-entry. And the most astonishing part is we don't have to look to the stars to find them. They are right here on Earth, and they are known as extremophiles. Extremophiles are organisms that don't just tolerate environments we consider hellish, they thrive in them. They are the ultimate survivors, pushing the boundaries of what we believed was possible for life. And in doing so, they provide the crucial proof of concept that makes panspermia a viable scientific idea. Let's meet a few of these incredible creatures. First, consider the unassuming tardigrade, also known as the water bear. These microscopic, 8-legged animals are arguably the toughest organisms we have ever discovered. Researchers have subjected them to the most extreme tests imaginable. They have been frozen to near absolute zero, heated to well over the boiling point of water, exposed to pressures 6 times greater than those at the bottom of the deepest ocean trench, and even desiccated to the point where they lose almost all their body water, entering a state called cryptobiosis where their metabolism shuts down entirely. Most incredibly, tardigrades have been taken into low Earth orbit and exposed to the complete vacuum of space and the full, unfiltered blast of solar cosmic radiation. And when brought back to Earth and rehydrated, they simply woke up, went about their business, and even reproduced. If any complex organism can survive an interplanetary journey inside a rock, it's the tardigrade. Then there is the bacterium Deinococcus radiodurans, a species that seems to defy the very laws of biology. Its name literally means strange berry that withstands radiation, and that is a massive understatement. A human being exposed to a dose of radiation around 5 grays would die within 2 weeks. Deinococcus radiodurans can shrug off a dose of 5,000 grays without breaking a sweat, and it takes 15,000 grays to kill it outright. It survives this incredible DNA shredding assault by having multiple copies of its genome and incredibly efficient repair mechanisms that can literally stitch its shattered genetic material back together within hours. For a microbe traveling through space, cosmic radiation is the single greatest threat. This bacterium demonstrates that such a threat is not necessarily a death sentence. But perhaps the most relevant analogues for potential Martian travelers are the microbes found in Earth's most Mars-like environments. In the hyper-arid McMurdo dry valleys of Antarctica, where it is so cold and dry that it's considered the closest thing to Mars on our planet, life still finds a way. Bacteria live not in lakes or streams, but inside the pores of rocks, surviving on minuscule amounts of moisture and weathering extreme temperature shifts and intense ultraviolet radiation. In the deepest, darkest mine shafts, where nutrients are scarce and pressure is immense, unique bacterial communities thrive completely isolated from the surface world. These resilient life forms show us that a planet doesn't need to be a lush, tropical paradise to host life. It just needs a tiny, protected niche where the hardiest of organisms can cling to existence. The existence of extremophiles transforms the panspermia hypothesis from a neat story into a testable scientific framework. It proves that the individual challenges of space travel, vacuum, radiation, temperature extremes are not insurmountable barriers for life. We have living examples right here at home that can endure each one of those conditions. The question is no longer, could anything possibly survive? But rather, given what we know can survive, is it actually happening? These incredible organisms are the living keys that unlock the possibility that life is not a fragile, fleeting phenomenon confined to a single planet, but a tenacious, adaptable force that could very well be spreading through the solar system, one rocky spaceship at a time. So if these incredible microbes provide the potential passengers, where do we find the physical evidence of their cosmic transportation system? The answer lies in rocks that have fallen from the sky, offering us tangible pieces of the puzzle. For centuries, meteorites were seen merely as curiosities, iron and stone from beyond our world. But modern science has revealed that some of these ancient space rocks are far more than simple debris. They are time capsules containing the very ingredients for life itself. The most compelling of these are a rare class known as carbonaceous chondrites. Unlike the more common iron or stony meteorites, carbonaceous chondrites are primitive, largely unchanged relics from the very dawn of our solar system, over 4.5 billion years ago. They never became part of a large planet where heat and pressure would have melted and purified them. Instead, they have been preserved in a deep freeze, retaining a complex cocktail of materials from the interstellar cloud that gave birth to our sun and planets. When scientists began to painstakingly analyze these rare meteorites, they made a breathtaking discovery. They are loaded with organic matter. This isn't about finding fossilized aliens, it's about finding the fundamental Lego blocks from which all biology is constructed. These meteorites have been found to contain a wide array of amino acids, which are the building blocks of proteins. They also contain nucleobases, which are the key components of DNA and RNA, the molecules that carry genetic information. They even contain sugars and fatty acids, which are essential for cell membranes and energy storage. In essence, these rocks carry a full, pre-packaged toolkit of organic chemistry, the same chemistry that is the foundation of every single living thing on Earth. The profound implication is that the universe appears to be preloaded with a bias for creating the materials of life. It seems that wherever you have the right conditions of gas, dust, and energy, like in the vast molecular clouds of space or around forming star systems, these complex organic molecules will naturally form. This process isn't magic, it's chemistry on a cosmic scale, and it suggests that the raw ingredients for biology are not rare at all, but are a common and widespread resource throughout the galaxy. Perhaps the most famous example of this is the Murchison meteorite, which fell in Australia in 1969. This event was a gift to science as the pristine fragments were collected quickly, minimizing contamination from Earth's own biology. The analysis of the Murchison meteorite revealed a stunning diversity of organic compounds. Scientists have identified over 90 different amino acids within it. What's absolutely fascinating is that only about 20 of these amino acids are used by life on Earth. The rest are completely non-biological. This tells us that the process that created them was undirected and universal, not a result of terrestrial contamination. It demonstrates that the abiotic or non-living chemistry of the cosmos can produce an incredible array of the very same molecules that life later selected and used. It's as if the universe handed life a menu of options, and life on Earth simply chose its favorites. Another remarkable specimen is the Tagish Lake meteorite, which fell on a frozen lake in Canada in 2000, providing another incredibly pristine sample. Its composition confirmed the findings from Murchison and added another layer of intrigue. Studies showed that these organic materials aren't just scattered randomly through the rock. Some are concentrated in tiny, microscopic globules that formed in the cold depths of space long before our solar system even existed. This tells us that this organic chemistry is not a local phenomenon of our own solar system, but a process that has been operating across the galaxy for billions of years. The evidence from these meteorites is powerful and direct. We are not theorizing about chemistry that might happen. We are holding the products of that chemistry in our hands. They are the physical, undeniable proof that the universe is inherently capable of manufacturing the complex organic building blocks of life. This doesn't prove that life itself traveled between planets, but it provides the strongest possible support for the first, crucial step of the panspermia hypothesis, that the seeds of life in the form of these sophisticated molecules are not only present out there but are being routinely delivered to planets like ours. When a young, barren Earth was being pummeled by asteroids and comets 4 billion years ago, it wasn't just being hit by destructive forces. It was also being seeded with a constant rain of life's potential, delivered right to its doorstep from the cosmic laboratory above. All of this background, the theories and the chemistry, set the stage for one of the most electrifying moments in the history of astrobiology. In August of 1996, the world was captivated by a press conference held by NASA and led by President Bill Clinton himself. The announcement was staggering. A team of scientists believed they had found evidence of ancient Martian life inside a meteorite. This wasn't a new rock. It was a specimen known as Allen Hills 84001, or ALH 84001 for short, discovered in Antarctica over a decade earlier. This meteorite, however, was special. Analysis had confirmed it was a piece of Mars, and it was ancient, dating back to a time when the red planet was warm and wet. The team, led by David McKay, presented a compelling, multifaceted argument built not on one single piece of evidence, but on 4 intriguing lines of investigation that together painted a tantalizing picture. The first and most visually striking clue was the presence of tiny, worm-like structures. Under powerful electron microscopes, the team revealed images of elongated forms that bore an uncanny resemblance to fossilized nanobacteria, many times smaller than any known earthly bacteria. To the public and many scientists, these looked for all the world like microscopic alien fossils. The second piece of evidence involved unique mineral formations. The team identified tiny crystals of an iron mineral called magnetite. On Earth, certain bacteria produce magnetite crystals of a very specific, pure size and shape to use as a compass, aligning themselves with Earth's magnetic field. The magnetite crystals found in ALH 84001 were not only identical in size and purity to those made by Earth's bacteria, but they were also found in chains as if they had been assembled inside a cell. The third line of evidence was chemical. The researchers found complex organic molecules known as polycyclic aromatic hydrocarbons, or PAH, concentrated within the fractures of the rock. While PAHs can form through non-biological processes, their specific concentration and distribution inside this Martian rock suggested to the team that they could be the decomposed remnants of ancient microorganisms. The final clue was the geological context. All of these features, the structures, the crystals, the PAHs, were found together in carbonate globules that had formed within cracks in the rock. The team argued that this close association pointed to a biological origin, as these globules could have acted as tiny, protected pockets where Martian microbes once lived and died. The announcement ignited a firestorm of excitement and controversy that continues to this day. The scientific community, while fascinated, immediately began poking holes in each piece of evidence. Skeptics argued that every single one of these features could be explained by non-biological abiotic processes. They pointed out that the worm-like structures were simply too small to theoretically contain the complex molecules necessary for life as we know it. They could be mineral artifacts or shapes formed by crystal growth. The magnetite crystals, while similar to those made by bacteria, can also be formed by certain non-biological chemical reactions under heat and pressure. The PA, they argued, were likely contaminants from the Antarctic ice where the meteorite had lain for thousands of years, or they could have been formed by inorganic chemistry on Mars itself. The central debate hinged on a fundamental principle of science. Extraordinary claims require extraordinary evidence. Could the team definitively rule out all non-biological explanations? For most of the scientific community, the answer was no. The evidence was highly suggestive but not conclusive. It was a masterclass in how science correctly functions. A bold claim is made, and the broader community rigorously tests it to see if it holds up. Decades later, the debate over LH84001 is still not fully settled. Subsequent research has both weakened and strengthened the original arguments. Some studies have shown that the magnetite crystals could indeed form without life, while others have doubled down, asserting that their specific properties are still best explained by biology. The case of the Martian meteorite serves as a crucial, ongoing lesson. It demonstrated that the search for life beyond Earth is incredibly difficult and that we must be meticulously cautious in interpreting data. It also proved that a single discovery is rarely a smoking gun, but rather a piece of a much larger puzzle. LH84001 didn't give us a definitive answer, but it profoundly changed the conversation. It forced scientists to develop more rigorous standards for identifying biosignatures. It ignited public passion for the search, and it left us with a haunting, powerful possibility that we may already be holding the fossilized remains of our celestial neighbors in our hands, even if we can't yet all agree on what we're seeing. But while the journey from Mars to Earth is a relatively short hop, the vast gulfs between stars present an entirely different set of challenges. The distances are so immense that they defy human intuition. The nearest star system, Proxima Centauri, is about 4.4 light-years away. That means even traveling at the speed of light, a journey that is impossible for any material object, it would take over 4 years to get there. For a rock moving at typical solar system velocities, such a trip would take millions of years. This raises a critical question: could anything possibly survive a voyage of such epic duration? The answer may lie not in lone rocks, but in far grander and more protected interstellar arcs. One compelling possibility involves our galaxy's great cosmic nurseries, giant molecular clouds. These are immense, faint regions of space, vast clouds of gas and dust that can span hundreds of light-years. They are the birthplaces of stars and planetary systems, and they are rich in the complex organic molecules we find in meteorites. Within these dense, dark clouds, there is a form of natural protection. The thick veils of dust and gas can act as a shield, dramatically reducing the levels of deadly cosmic radiation that would otherwise sterilize any biological material. If life could originate or find refuge within the sheltered pockets of such a cloud, the entire cloud itself could act as a slow-moving vehicle. As it drifts through the galaxy over millions of years, it could potentially transfer the raw ingredients of life, or even dormant life itself, from one emerging star system to the next. It's a concept that transforms these nebulous regions from simple star factories into potential galactic conduits for biological material. An even more fascinating and robust interstellar delivery system could be rogue planets. These are worlds that were once part of a star system but were violently ejected by gravitational interactions with larger planets, sent careening into the dark, empty spaces between the stars. Astronomers now believe there could be billions, even trillions of these nomad planets wandering our galaxy alone. A life-bearing planet ejected from its system would not necessarily become a frozen tomb. If it had a subsurface ocean, like the one we suspect exists on Jupiter's moon Europa, that water could remain liquid for billions of years due to heat generated by the radioactive decay of elements in its core, or by gravitational tidal forces if it retained a moon. In such a protected, warm, and dark aquatic environment, life that had already begun could potentially continue to thrive, completely isolated from the need for a sun. This rogue planet would then become a self-contained interstellar spaceship, carrying its entire biosphere with it across the galaxy. The chances of such a world ever colliding with another planet to seed it are astronomically small, but given the billions of years and the countless number of rogue planets, it might only need to happen once in a galaxy to spread life widely. For smaller objects like comets or large asteroid fragments, the key to surviving an interstellar journey is a combination of size and dormancy. A comet several kilometers in diameter has a tremendous amount of interior volume that is completely insulated from the harsh environment of space. While its surface is blasted by radiation and its tail glows from sublimating ice, the core deep within can remain pristine, a frozen time capsule preserving whatever was trapped inside when it formed. We know from studying comets in our own solar system that they are rich in organic compounds and water ice. A microbe trapped in that deep freeze would enter a state of suspended animation, its metabolism halted completely. In such a state, time becomes almost irrelevant. A million-year journey is no different from a 1,000-year journey if all biological processes are stopped. The organism wouldn't be surviving the trip in an active sense. It would simply be pausing itself, waiting for the journey to end and for warmer conditions to revive it. The real challenge is the initial ejection from a star system and the final delivery to a new one. But as we've seen with pseudo-panspermia, the physics for that local transfer is sound. Scaling it up to an interstellar level is about finding the right vehicle that can provide protection for the incomprehensibly long durations required. Whether it's within the relative safety of a molecular cloud, the deep ocean of a rogue planet, or the icy heart of a giant comet, the universe may be filled with countless slow-moving biological arcs, each on a million-year journey to a potential new home. To truly appreciate the plausibility of life hitching a ride between worlds, we need to travel back in time over 4 billion years to the chaotic and violent nursery where our solar system was born. This was not the stable, orderly clockwork of planets we see today. It was a colossal construction zone, a swirling disk of gas and dust around our young sun, filled with countless planetesimals, rocky and icy bodies constantly colliding, merging and shattering. In these first few 100 million years, gravity was the great architect pulling these fragments together to form the protoplanets, but the process was incredibly violent. Imagine a celestial demolition derby on an unimaginable scale, with massive impacts occurring not as rare catastrophes, but as regular, everyday events. It was within this frenetic environment of constant collision, an exchange, that the fundamental mechanics of panspermia became not just possible, but almost inevitable. The solar system was a single, interconnected system, with material from the inner and outer regions constantly being mixed and flung across vast distances. This period of extreme cosmic violence reached its peak during an epoch known as the Late Heavy Bombardment, which occurred roughly between 4.1 and 3.8 billion years ago. The name itself doesn't quite capture the sheer ferocity of this time. It was less a bombardment and more a celestial artillery barrage of apocalyptic proportions. The entire inner solar system, Mercury, Venus, Earth, and Mars, was subjected to a relentless rain of impactors. The evidence of this is written clearly on the face of the Moon. Its heavily cratered highlands are the permanent scars from this ancient cataclysm. Earth, being larger and with stronger gravity, would have received an even greater number of impacts. Any early oceans would have been repeatedly flash-boiled by asteroids the size of small countries slamming into the planet, releasing enough energy to sterilize the surface over and over again. For any life trying to get a foothold on the surface, this was an existential threat. Yet, for the theory of panspermia, this period of extreme destruction also created the perfect conditions for distribution. Every one of those colossal impacts was a potential launch event. When a large asteroid or comet struck a planet, the energy was so immense that it could vaporize rock and send plumes of molten material hurtling into space. But crucially, not all of the ejected material was vaporized. Computer simulations and studies of impact craters show that rocks from near the surface, particularly on the edges of the impact zone, could be spalled off, blasted into space almost intact while being subjected to lower peak temperatures and pressures. The physics is similar to skipping a stone across water. The immense shock wave from the impact propagates through the crust and can catapult significant fragments clear out of the planet's gravity well. This process effectively turned every major impact into a natural mass driver, firing countless potential biological lifeboats into interplanetary space. The beauty of this system lies in its interconnectedness. A rock blasted off Mars by one impact could become a meteoroid orbiting the Sun, its path gradually altered by gravitational tugs from other planets over thousands or millions of years. Eventually, its orbit might intersect with that of Earth, leading to a final, fiery descent through our atmosphere. We know for a fact that this material exchange happened on a massive scale. The meteorites we have identified as coming from Mars and the Moon are the surviving proof of this cosmic shipping network. The early solar system was not a collection of isolated, independent worlds. It was a single, dynamic environment where planets regularly swapped material. During the late heavy bombardment, the traffic was at its heaviest. The chances of a life-bearing rock leaving one habitable world and successfully landing on another were dramatically higher simply because so many rocks were making the journey. It was a time of both incredible peril and incredible opportunity, a period where cataclysmic destruction and the seeding of new life were two sides of the same cosmic coin. All of this cosmic theory and ancient history is compelling, but the true test of any scientific idea lies in direct modern experimentation. To move the panspermia hypothesis from a plausible scenario to a supported theory, we needed to take life itself and subject it to the ultimate challenge, the unforgiving environment of space. This is precisely what scientists have been doing for decades, utilizing one of humanity's greatest engineering achievements as their laboratory, the International Space Station. The results of these experiments have been nothing short of revolutionary, fundamentally reshaping our understanding of life's limits and, in turn, dramatically boosting the credibility of panspermia. The most famous of these investigations is the ongoing EXPOSE project, a series of European Space Agency experiments that are as brutal as they are brilliant. Scientists mounted small containers like metal suitcases to the exterior of the space station. Inside these containers were samples of some of Earth's hardiest organisms, bacteria, fungi, lichens, and even tiny tardigrades. Then the containers were opened, exposing these living passengers directly to the void. For months, and in some cases years, these microbes were subjected to a simultaneous onslaught of every hazard space has to offer. The complete vacuum, which causes violent desiccation, extreme temperature fluctuations ranging from bitter, deep space cold to scorching heat when in direct sunlight, and perhaps most critically, the full, unfiltered barrage of solar ultraviolet radiation and cosmic rays. It was a comprehensive, real-world stress test of the absolute worst-case scenario for an interstellar journey. When the samples were eventually brought back inside the station and returned to Earth for analysis, the results stunned the scientific community. A significant number of the organisms not only survived but were able to revive, metabolize, and reproduce after their ordeal. Certain species of bacteria, particularly those known for forming protective endospores, showed remarkable resilience. But the true champions were, unsurprisingly, the tardigrades. These microscopic animals demonstrated an almost supernatural ability to endure. When faced with the desiccating vacuum, they entered their cryptobiotic state, curling into a lifeless-seeming ton, and simply waited it out. Even after 18 months of continuous exposure, a substantial portion of them were successfully rehydrated in the lab and simply went about their day as if nothing had happened. They had effectively proven that complex multicellular life can, in fact, weather the conditions of space. Perhaps the most significant finding was the critical importance of shielding. While direct exposure to solar UV radiation was almost always fatal, organisms that were placed in simulated meteorite conditions, embedded just millimeters beneath the surface of a rock or a layer of clay, survived at vastly higher rates. The rock acted as a superb radiation shield, blocking the most damaging wavelengths while also buffering against the extreme temperature swings. This single finding provides the crucial experimental link that connects the theory of pseudo-panspermia to observable reality. It demonstrates that while space is indeed lethally hostile to exposed life, the interior of a meteoroid provides a surprisingly effective sanctuary, a kind of natural spaceship that can preserve its biological cargo for astonishing lengths of time. These experiments have given us something priceless: empirical data. We are no longer just theorizing that life might survive. We have direct evidence that specific, known organisms do survive. This transforms the conversation from abstract possibility to a matter of probability and time. We now have a catalogue of extremophiles whose survival thresholds we have measured against the known parameters of space travel. We can input this data into models that simulate a journey from Mars to Earth, or even a longer voyage within a comet, and calculate the odds, and those odds are looking increasingly favorable. The resilience of life, as demonstrated on the exterior of the International Space Station, suggests that the galaxy may not be a sterile desert separating isolated oases of life, but rather a vast ocean crisscrossed by natural vessels, each carrying the potential to seed new worlds with a biological heritage that might stretch back billions of years and across untold light years of space. Given the very real possibility that microorganisms could survive a journey between worlds, a critical question emerges for our own spacefaring species. Are we, in our exploration of the solar system, becoming an unwitting vector for a modern-day panspermia event? This isn't a theoretical worry. It's a profound ethical and scientific responsibility that space agencies take extremely seriously. The field dedicated to this is called planetary protection, and its core mission is to prevent biological contamination both forward and backward. It's the practical, real-world application of the panspermia hypothesis, and it's a testament to how seriously science treats this idea. Forward contamination is the concern that we might accidentally transport earthly microbes to other celestial bodies. Imagine sending a rover to drill into the subsurface ice of Mars or to sail the hydrocarbon seas of Titan. If that spacecraft weren't meticulously cleaned, it could carry hardy extremophiles from our own planet. Upon arrival, these terrestrial stowaways could not only compromise the scientific integrity of the mission by making it impossible to determine if any discovered life is truly alien, but could also potentially invade and disrupt a pristine extraterrestrial ecosystem. To prevent this, space agencies like NASA and the European Space Agency maintain incredibly strict sterilization protocols for any spacecraft destined for a special region, a place with a potential for life, like Mars or the icy moons of Jupiter and Saturn. The process is exhaustive. Components are assembled in pristine, giant clean rooms where air is constantly filtered, and technicians wear head-to-toe bunny suits to prevent human skin cells and bacteria from contaminating the hardware. The spacecraft itself is often baked in a giant oven called a heat sterilization unit at temperatures high enough to kill even the most resilient bacterial spores. Every single part, down to the individual bolts, is meticulously cleaned with alcohol and other sterilizing agents. The goal is to reduce the total microbial load on the spacecraft to an astonishingly low level, ensuring the probability of contaminating another world is virtually zero. This isn't just about good cleaning, It's about preserving the natural state of other worlds for scientific study and honoring our role as responsible explorers of the cosmos. The flip side of this coin is back contamination, a concept that sounds like it's straight out of a science fiction thriller but is treated with utmost gravity. This is the hypothetical risk of bringing extraterrestrial biological material back to Earth, where it could potentially pose a threat to our biosphere. The most famous example of this protocol in action was during the Apollo missions. When the first astronauts returned from the moon, no one could say for certain that the lunar surface was completely sterile. They were immediately quarantined in a specially designed mobile quarantine facility and then transferred to the Lunar Receiving Laboratory in Houston, where they lived in isolation for 21 days. The rock samples they brought back were also kept in strict biological containment until they could be analyzed and deemed non-hazardous. While we now know the moon is lifeless, the same cautious approach is being planned for future missions that will return samples from places with a high potential for past or present life, most notably Mars. The proposed Mars sample return mission involves an intricate multi-step process where the samples will be sealed inside a series of containers on the Martian surface, launched into orbit, and then captured by another spacecraft for the journey back to Earth. Upon arrival, they won't be delivered to a standard lab. They will be received in a maximum security biosafety level 4 facility, similar to those used to study the world's most dangerous pathogens like Ebola. This facility would be designed to contain any potential organism completely, protecting both our environment and the pristine scientific value of the samples themselves. These rigorous protocols are a powerful acknowledgement of the panspermia hypothesis. By taking such extreme measures to prevent contamination, our space agencies are essentially admitting that the interplanetary transfer of life is not just a wild theory, but a credible enough possibility that we must actively guard against it, ensuring that our search for life beyond Earth is conducted with both wonder and wisdom. This incredible dance between possibility and precaution brings us to one of the most profound and haunting questions in all of science. If life is so tenacious and the universe so vast and ancient, then where is everybody? This is the essence of the Fermi paradox, the startling contradiction between the high probability of extraterrestrial intelligence and the complete lack of any observable evidence for it. The panspermia hypothesis doesn't just add another layer to this mystery. It offers a fascinating and potentially terrifying new set of solutions. If life can indeed spread naturally between star systems, as lithopanspermia or interstellar clouds suggest, then the universe should be teeming with life. The process wouldn't be limited to one lucky planet. It would be a galactic chain reaction. A single biosphere in a single star system could, over billions of years, seed thousands of nearby systems with its biological legacy. This concept, known as galactic panspermia, would make life not just common but inevitable and widespread. In such a scenario, the silence we hear from the cosmos becomes even more deafening. The paradox deepens. If life is everywhere, then intelligent, technological civilizations should also be common. Their activities, whether intentional or not, should leave some detectable mark on the galaxy, radio signals, megastructures, or other signs of their presence. Yet we see nothing but a quiet, undisturbed emptiness. This suggests that something is actively preventing life from reaching that technological stage or from making its presence known. This something is often called the Great Filter, a barrier so formidable that almost no life can get past it. Panspermia forces us to ask a chilling question: is the filter behind us, or is it still ahead of us? Perhaps the filter is behind us, and the spontaneous origin of life is the insurmountable barrier. Panspermia would neatly resolve this by saying that the filter wasn't on Earth. The miracle of abiogenesis happened only once, in one incredibly rare and special environment somewhere else in the galaxy, and the rest of us are just the beneficiaries of that single cosmic fluke. We aren't the product of a universe overflowing with life. we are the lonely heirs to a legacy from a world that no longer exists. This would mean the galaxy might be filled with planets seeded by that one original biosphere, but none of them ever managed to spark life on their own. We could be living in a quiet, sterile galaxy where every living thing is a cousin, all descendants of that one incredible Genesis event, but separated by such vast distances and time that we are effectively alone. The more unsettling possibility is that the great filter is still ahead of us. Maybe the development of complex, intelligent life is common, but the emergence of a technological civilization is what inevitably leads to self-destruction. Perhaps every species that reaches our level of advancement soon after discovers the tools of its own annihilation, whether through nuclear war, uncontrolled artificial intelligence, or ecological collapse, and vanishes before it can ever announce its presence to the stars. In this grim view, the silence of the universe is a cemetery quiet, a warning from an empty galaxy that the final step to the stars is a cliff that no one survives. But there is another, even more mind-bending resolution that panspermia offers, one that connects back to the idea of directed panspermia. What if we don't see anyone because the galaxy is being carefully managed? Imagine a scenario where a first, ancient intelligence arose billions of years before us. This civilization, having mastered interstellar travel and perhaps even biological engineering, embarked on a project of cosmic-scale gardening. They could have seeded countless promising worlds with a standardized biological package, a starter kit for life designed to evolve along a predictable path. This would explain why we find the universe so bio-friendly. It was literally made that way. The building blocks are universal because the gardeners designed them to be. In this zoo hypothesis or planetary park model, our solar system, and indeed our entire galaxy, could be a protected wilderness area, deliberately kept pristine and free from outside interference so that life can develop naturally. Our radio signals might be silently monitored, but no one will answer. Making contact would ruin the experiment. Our seeming isolation wouldn't be a sign of our insignificance, but rather the ultimate mark of being part of something incomprehensibly vast and carefully curated. We wouldn't be alone. We would be the subject of the most grand and patient observation project in the history of the cosmos. This opens up an even more profound possibility. What if the life delivered to a planet wasn't just a variation on our own theme of carbon and water, but something entirely alien? We tend to assume that life everywhere would follow the same basic biochemical rules we see on Earth: carbon-based molecules dancing in a water solvent. But the universe is a chemist of infinite creativity, and it's entirely possible that the spark of life could ignite in environments so strange they would be utterly hostile to us. If panspermia is a real process, then the seeds it scatters might not all be from the same tree. We could be receiving visitors based on a completely different operating system. The most discussed alternative to our carbon-based or organic life is the possibility of silicon-based biology. On the periodic table, silicon sits directly below carbon, which means it shares some similar chemical properties. Like carbon, silicon can form 4 bonds with other atoms, making it a potential backbone for complex molecules. In the intense heat and pressure of some alien worlds, silicon-based compounds might be more stable and better suited for building the intricate structures necessary for life. Imagine a planet where the sands themselves are alive, with complex silicates forming structures analogous to our proteins and cell membranes, thriving in environments where carbon-based molecules would simply fall apart. A meteorite carrying such a silicon-based microbe would be utterly alien to our world. It might not even interact with our biochemistry, leaving no trace for us to find, or it might find our oxygen-rich atmosphere to be instantly corrosive and fatal. Beyond the backbone of life, there's the question of the liquid that makes all the chemistry possible: the solvent. On Earth, that solvent is water, and its unique properties are essential for every known life form. But what about a world that is far too cold for liquid water, like the surface of Saturn's moon Titan? There, rivers and lakes are filled with liquid methane and ethane, flowing at temperatures around -180 degrees Celsius. In such a frigid environment, the chemical reactions that power life would happen agonizingly slow by our standards. But if life did arise there, it would likely use a completely different set of molecules, perhaps built around lipids and other compounds that remain flexible and reactive in that deep cold. An organism adapted to a methane solvent would find Earth's oceans to be a boiling, destructive acid bath. If panspermia delivered such a creature to our planet, it would perish instantly, leaving behind no recognizable fossil or chemical signature. We might have already received such visitors and simply lacked the framework to even recognize them as life. This concept completely reframes the search for life elsewhere. If we are only looking for life as we know it for biomarkers like oxygen, methane, and water, we might be blinding ourselves to a much wider, weirder biological universe. A truly universal panspermia process wouldn't just be spreading Earth-like life. It would be a delivery service for every possible flavor of biology that the laws of physics and chemistry allow. One stellar nursery could be seeding planets with carbon-based life, while another, with a different composition of elements, might be the birthplace of exotic arsenic-based or nitrogen-based organisms. The challenge for us, then, is not just to find life, but to expand our very definition of what life is. It forces us to ask if our own biochemistry is the rule, or merely one single, local example of a phenomenon that can manifest in countless different forms across the cosmos. The silent void we perceive might not be empty at all. It could be buzzing with biological activity that is, for now, completely invisible to our carbon-based senses. So if the raw ingredients for life are being delivered throughout the cosmos, how do we get from those simple organic molecules to the intricate, self-replicating systems that define a living cell? This brings us to one of the most compelling ideas in all of origin of life research, a concept that could perfectly bridge the gap between cosmic chemistry and earthly biology. It's called the RNA world hypothesis, and it suggests that before the sophisticated DNA and protein-based life we see today, there was a much simpler, more primitive stage where a single, multitasking molecule ruled the world. This molecule is RNA, or ribonucleic acid, and its unique properties make it the ideal candidate for the very first spark of evolution. In modern cells, we see a clear division of labor. DNA acts as the long-term, stable library of genetic information, safely storing the instructions for building an organism. Proteins are the workforce, the enzymes that carry out almost every chemical reaction necessary for life. But this system presents a classic chicken and egg problem. You need DNA to provide the code to make the proteins, but you need specific proteins to unravel and replicate the DNA. So which came first? The RNA world hypothesis offers an elegant solution. RNA can do both jobs. An RNA molecule is not just a passive messenger. Certain types can act as enzymes themselves, catalyzing chemical reactions, including the replication of other RNA strands. This means a single type of molecule could have both carried genetic information and performed the metabolic work to copy itself, all without needing DNA or proteins. It could have been both the blueprint and the builder, a one-molecule show that kick-started the entire process of evolution. Now, here's where the concept of panspermia weaves this theory into an even grander cosmic narrative. The spontaneous formation of a long, functional RNA molecule in the primordial soup of early Earth is an incredibly complex and statistically challenging event. It requires the right nucleotides to form and then link together in a specific sequence that somehow also possesses a useful function like self-replication. But what if that most difficult step didn't happen here? What if the universe itself has been acting as a vast probiotic chemistry lab for billions of years? We know that the fundamental building blocks of RNA, the nucleobases like uracil and adenine, and the sugar ribose have been found in carbonaceous chondrite meteorites. The Murchison meteorite, for instance, contained uracil, a key component of RNA. This tells us that the universe isn't just making amino acids, it's manufacturing the specific ingredients needed for an RNA world. The sheltered environments within molecular clouds or on the surfaces of icy asteroids could provide the perfect conditions for these ingredients to slowly and patiently assemble into more complex structures, far away from the violent, unpredictable conditions of a young planetary surface. Imagine a scenario where the interiors of comets or the clay-rich surfaces of asteroids acted as microscopic test tubes. Over millions of years in the cold and the dark, with energy supplied by cosmic radiation or the gentle warmth of radioactive decay, these simple organic molecules could have linked together. They might have formed short RNA chains or even more primitive replicating molecules that served as a precursor to RNA. These wouldn't be living organisms, but rather what scientists call protocols, self-organizing, self-replicating chemical systems that represent the threshold of life. Then, as we've discussed, a massive impact on that asteroid or a gravitational nudge sent that material on a journey. When it finally crashed into a young, water-rich Earth, it wouldn't just be delivering a box of spare parts. It could have been delivering a partially assembled engine, a set of molecular tools that were already well on their way to becoming life. This dramatically shortens the window of time life had to arise on our planet. Instead of starting from absolute scratch with simple chemistry, Earth may have been inoculated with an advanced starter kit, a head start that allowed the RNA world to establish itself almost as soon as our planet was ready. In this view, panspermia isn't just about delivering life, but about delivering the most critical and hardest to form precursors to life, effectively giving evolution a massive cosmic boost and making the emergence of a biosphere not just a local event, but a fundamental and widespread process in a universe that is inherently and creatively bio-friendly. For centuries, our view of the cosmos was fundamentally limited. We only knew of one star system with planets our own. The idea of life traveling between worlds, while fascinating, was confined to the theoretical interactions between Mars, Earth, and Venus. But that entire paradigm has been completely overturned. The last 2 decades have witnessed a revolution in astronomy, one that has profound implications for the panspermia hypothesis. We now know that planets are not the exception but the rule. The Kepler Space Telescope and other observatories have revealed that nearly every star in the sky is likely orbited by at least one planet, with our galaxy alone containing billions upon billions of them. This staggering abundance completely changes the math. It transforms panspermia from a speculative idea about a few neighboring rocks into a potential galaxy-wide phenomenon, a process operating on an almost unimaginable scale. This shift is most dramatically illustrated when we find planetary systems that are nothing like our own. Our solar system, with its widely spaced planets, is actually something of an outlier. Many of the most common systems we've discovered are compact, with multiple worlds orbiting incredibly close to their star. The poster child for this new reality is the TRAPPIST-1 system, located about 40 light-years away. This system features not 1, not 2, but 7 Earth-sized planets orbiting an ultra-cool red dwarf star. The entire system is smaller than the orbit of Mercury in our own solar system. The planets are so close together that from the surface of one, you could often see the neighboring worlds in the sky, not as faint points of light, but as visible disks, their geological features perhaps discernible to the naked eye. This proximity completely redefines the concept of interplanetary travel. In a system like TRAPPIST-1, the mechanics of lithopanspermia move from a billion to one long shot to a near certainty over astronomical time. An impact powerful enough to eject a rock from one planet would have a vastly higher probability of that rock being captured by the gravitational pull of one of its immediate neighbors. The journey between these worlds wouldn't take millions of years, it could take mere decades or even just years. This drastically shortens the survival time for any microbial stowaways, making their successful transfer almost a trivial matter compared to the epic voyage from Mars to Earth. If just one of those 7 planets developed life, or even just the complex probiotic chemistry for life, it could have easily spread to all the others, turning the entire system into a single, interconnected biological sanctuary. We could be looking at entire solar systems that are not just habitable but fully inhabited, sharing a common family tree of life that has been swapping genes across space for billions of years. This discovery of exoplanets also expands the potential habitats for life in ways that challenge our Earth-centric views. We've found super-Earths, planets larger than our own, that might have more stable geology and longer-lasting magnetic fields to protect life. We've discovered hot Jupiters whose large moons could potentially host subsurface oceans. We've even identified Hycean worlds, a proposed class of planet covered in a global ocean with a hydrogen-rich atmosphere that could be conducive to certain forms of life. Each new type of world adds another potential node in a galactic panspermia network, a life-bearing planet being ejected from its star system to become a rogue world, as we discussed earlier, becomes an even more powerful idea when we realize there are likely more rogue planets in the galaxy than there are stars. These dark, nomadic worlds could be the ultimate long-distance carriers, preserving and transporting life between stellar islands over billions of years. The sheer number of exoplanets doesn't just make panspermia more likely, it reframes our entire search for life. If life can spread so readily, then we shouldn't necessarily be looking for the one perfect Earth twin. Instead, we should be looking for the most well-connected systems, the ones where planetary proximity would facilitate the easiest exchange of material. Finding a biosignature like the combination of oxygen and methane in an exoplanet's atmosphere would be momentous, but if we found that same specific biosignature on multiple planets within the same compact system, that would be the most powerful evidence yet for panspermia. It would suggest we are not looking at several independent origins of life, but one single origin that has successfully colonized its entire stellar neighborhood. The discovery of exoplanets has given us a new cosmic map, and on that map, the pathways for life are now drawn in bold, connecting stars and worlds into a web of biological potential that stretches across the entire galaxy. Yet for all its compelling narrative and experimental support, the panspermia hypothesis is not without its significant detractors, and a robust scientific debate continues to this day. One of the most common and powerful criticisms leveled against it is that it doesn't actually solve the fundamental mystery of life's origin, it simply relocates it. Skeptics argue that pushing the event to another planet or even another star system does nothing to address the immense challenge of abiogenesis. It merely moves the goalposts to a place we cannot currently observe or study. This, they contend, is a classic God of the Gaps argument, using an unknown elsewhere to explain an unknown here. By invoking panspermia, we are potentially bypassing the difficult but crucial work of understanding how non-living matter can spontaneously organize into a living, replicating system under the natural conditions of the early Earth or another similar world. The core miracle of that initial spark remains, whether it happened in a Martian hot spring, on an icy moon, or in the depths of a molecular cloud. Critics maintain that until we can demonstrate a plausible pathway for abiogenesis somewhere, the hypothesis merely adds an unnecessary and unprovable step to the equation, complicating the story without providing a definitive answer. Another major point of contention revolves around the sheer statistical improbability of each individual step in the interstellar panspermia process, even with the protective shield of a rock. While we have evidence that microbes can survive certain stages of the journey in isolation, the critics ask whether any organism could possibly survive the entire multi-million-year cascade of events from ejection to transit to atmospheric entry and final impact. The odds against a single microbe successfully completing this epic voyage are astronomically low. First, the initial impact must be powerful enough to eject a rock into space, but not so violent that it completely vaporizes the rock or sterilizes its interior with heat and shock pressure. Then, this ejected fragment must happen to be on a trajectory that not only escapes its home star's gravity, but also eventually intersects with another habitable planet. This journey through interstellar space, even inside a rock, exposes the organism to constant cumulative doses of cosmic radiation over millions of years. While a large meteoroid offers protection, it is not a perfect shield, and the slow buildup of radiation damage could still degrade complex organic molecules beyond repair over such immense timescales. Then comes the final, fiery obstacle of atmospheric entry. While we know the interiors of large meteorites can remain cool, the process is incredibly violent and unpredictable. The rock must be large enough to protect its core, but not so large that its impact creates a sterilizing fireball. It must land in a location that is immediately hospitable, a body of water or a nutrient-rich environment, giving the dormant passengers a chance to awaken and propagate. For every one successful journey, there could be billions of failures where rocks miss their target entirely, burn up on entry, or land in a barren desert or frozen wasteland. When you multiply all these individual low probabilities together, the overall chance of a successful transfer of life between star systems seems vanishingly small. Detractors argue that while not physically impossible, it is an incredibly inefficient and unlikely process, one that probably cannot account for the widespread distribution of life, especially when compared to the possibility of independent origins on countless suitable worlds. Furthermore, there is the challenge of what biologists call planetary compatibility. Even if a microbe from another world did survive the journey and land in a hospitable pond on Earth, would it even be able to function? Life on Earth, from the simplest bacterium to the largest whale, is built on a wonderfully intricate and interconnected biochemical system. Our genetics use a specific set of nucleotides. Our proteins are made from a specific set of 20 amino acids. Our cellular machinery is based on a specific chiral handedness, with all our biological molecules being left-handed. An organism that evolved on another world, under a completely different set of evolutionary pressures and chemical conditions, might use an entirely different biochemical alphabet. Its genetic code might be unreadable to earthly life, and its metabolic processes might be completely incompatible with our available nutrients. It could be as foreign as a computer plug trying to fit into a power outlet designed for a different country's voltage and shape. A Martian microbe landing on early Earth might simply find no food it could eat, no way to replicate, and would die out immediately, leaving no trace. For panspermia to work as a seeding mechanism, it requires not just the transfer of life, but the transfer of a very specific type of life that is pre-adapted to the conditions of its new home, which adds yet another layer of improbability to the entire concept. These criticisms are not meant to dismiss the panspermia hypothesis outright, but to apply the necessary scientific rigor and healthy skepticism that drives all good research forward. The debate itself is a testament to the complexity of the question and the need for ever more sophisticated evidence. Proponents of panspermia counter these arguments by suggesting that while each step is improbable on its own, we are not talking about a single event. We are considering the outcomes of a universe that is incomprehensibly vast and ancient, with countless trillions of opportunities for it to happen. Given enough time and enough chances, even the most unlikely events become inevitable. They also point to the universality of the genetic code and the building blocks of life as potential evidence for a common source, suggesting that if life started independently multiple times, we might expect to see a much greater diversity in its fundamental biochemistry. The conversation continues, pushing scientists to design better experiments, search for more definitive evidence on Mars and in the atmospheres of exoplanets, and refine our understanding of life's incredible resilience. This ongoing dialogue is not a weakness of the idea, but rather the very engine of scientific discovery, constantly testing the boundaries of what we know and what we dare to imagine. To truly put the theory of panspermia to the test, scientists have moved beyond observation and into the realm of direct experimentation, recreating the extreme conditions of an interplanetary journey right here in the lab. One of the most violent stages of this epic voyage is the very first one, ejection from a planet's surface. Researchers have used high-powered gas guns and explosive-driven shock tubes to simulate the immense pressures and G-forces a microbe would experience when a massive asteroid impact launches a rock into space. In these dramatic tests, containers holding various types of bacteria are subjected to shock pressures exceeding 400,000 times Earth's atmospheric pressure, a force far greater than what is needed to launch material from Mars. The results are astonishing. Not only do a significant number of the bacteria survive, but some hardy species, like the radiation-resistant Deinococcus radiodurans, show almost no reduction in viability at all. These experiments demonstrate that the initial blast off a planetary surface, while apocalyptic in scale, is not an insurmountable barrier for life, provided it is nestled safely within a rocky shield. Once a microbe has escaped its home world, it faces the long, silent cruise through the vacuum of space. To study survival in this environment, scientists have turned to the ultimate laboratory, the International Space Station. Experiments like the European Space Agency's EXPOSE project have placed hundreds of samples of bacteria, fungi, lichens, and tardigrades in specially designed containers on the exterior of the station, directly exposing them to the harsh realities of space for months or even years at a time. These samples endured the complete vacuum, extreme temperature fluctuations from bitter cold to scorching heat, and the full, unfiltered barrage of solar ultraviolet radiation and cosmic rays. The findings were a revelation. While direct exposure to solar UV radiation proved almost universally fatal, organisms that were artificially shielded by just a thin layer of rock or clay, simulating being embedded inside a meteoroid, survived at remarkably high rates. Tardigrades, true to their legendary reputation, proved to be the ultimate survivors, with many individuals reviving and reproducing normally after their 18-month stint in the void. These studies provide the crucial experimental link, proving that the interior of a space rock provides a sufficient sanctuary to preserve biological material for the long durations required for interplanetary travel. The final, fiery hurdle of atmospheric re-entry has also been rigorously tested. Scientists have used aerodynamically shaped capsules loaded with biological samples, including fossilized microbes within artificial meteorites, and launched them on small rockets or fired them from high-velocity guns to simulate the intense heat and pressure of plunging through an atmosphere. In one landmark study, a slate rock containing the fossilized remains of ancient diatoms was affixed to the heat shield of a Russian spacecraft. After a full re-entry, the rock was recovered and examined. While the exterior was charred and melted, the interior remained cool enough that the delicate fossil structures were perfectly preserved. Another experiment involved loading bacteria into the cavities of mock meteorites made of basalt and granite, which were then subjected to hypervelocity impacts into water or sand to simulate the final landing. The results consistently show that while the outer layers of a meteorite ablate away, creating the fiery streak of a shooting star, the core can remain a cool, protected refuge. The organisms inside are not baked, they are insulated, surviving the ordeal completely unscathed. Together, these diverse experiments form a powerful chain of empirical evidence, proving that each individual stage of the panspermia process, ejection, transit, and re-entry, is not only physically possible but well within the astounding survival limits of life itself. This profound shift in perspective, from life as a rare anomaly to a potentially widespread cosmic phenomenon, forces us to revisit one of the most famous attempts to quantify our place in the universe, the Drake equation. Conceived by astronomer Frank Drake in 1961, this formula isn't meant to provide a single, definitive answer, but rather to frame the discussion and identify the key variables we need to understand. The equation is a series of factors multiplied together, estimating the number of active, communicative extraterrestrial civilizations in our Milky Way galaxy. It starts with the rate of star formation, then multiplies that by the fraction of stars that have planets, the number of planets per star that can potentially support life, the fraction of those where life actually appears, the fraction where life develops intelligence, the fraction where that intelligent life develops technology that releases detectable signs into space, and finally, length of time such civilizations release those detectable signals. For decades, the most uncertain and debated terms have been those in the middle, particularly the fraction of habitable planets where life actually arises, often denoted as F sub L. This factor has been a huge question mark, a placeholder for the mystery of abiogenesis. If the origin of life is an incredibly difficult, 1 in a billion fluke, then F sub L would be very, very small, suggesting that even in a galaxy brimming with planets, we might be profoundly alone. The panspermia hypothesis completely rewrites the assumptions behind this crucial variable. If life can spread naturally from one habitable world to another, then F sub L is no longer about the independent origin of life on each individual planet. Instead, it becomes a question of the origin of life within an entire star cluster or a gravitationally linked group of systems. This distinction is everything. Let's say that the spontaneous generation of life from non-living matter is in fact an extraordinarily rare event, happening only once in 100,000 star systems. In a traditional Drake equation model, that would mean only 1 in 100,000 habitable planets would actually host life. But if that one rare event occurs in a system with multiple habitable worlds, like TRAPPIST-1, or if its biological material can easily jump to neighboring star systems through mechanisms like rogue planets or shielded travel within molecular clouds, then that one genesis event could seed not just one, but dozens, hundreds, or even thousands of planets. The value of F sub L would skyrocket. The probability of a habitable planet hosting life would no longer be tied to the near miracle of abiogenesis happening right there. It would simply be a function of whether that planet has ever been within the delivery range of a life-bearing meteorite or comet from an already inoculated world. In this panspermia-influenced model, life becomes a contagion, spreading through the galaxy and infecting suitable planets wherever it finds them. The equation shifts from estimating the odds of a spark to mapping the reach of a flame. This doesn't just tweak the Drake equation, it fundamentally alters the landscape of possibilities it describes. A higher F sub L directly increases the estimated number of intelligent civilizations, making a crowded, lively galaxy a much more statistically probable outcome. It strengthens the weight of the Fermi paradox, the question of where everybody is, because it suggests that the great filter, the barrier that prevents life from reaching a detectable stage, is less likely to be the initial origin of life itself. If panspermia is efficient, then the filter preventing us from seeing other civilizations must lie further down the line, perhaps in the development of intelligence or the long-term survival of technological species. This introduces a more sobering possibility. The challenge might not be becoming alive, but staying alive long enough to become a spacefaring civilization. Alternatively, a panspermia-rich galaxy could support the hypothesis that technological civilizations are common, but they are either deliberately avoiding contact or using forms of communication we are yet to recognize or detect. By raising the value of F sub L, panspermia forces us to confront the later terms in the Drake equation with greater urgency. pushing the mystery of our solitude away from biology and toward the realms of sociology, technology, and long-term survival. It suggests that if we are alone, the reason is likely more complex and perhaps more tragic than a simple lack of initial ingredients. While the idea of fully formed organisms traveling between stars captures our imagination, a far more scientifically grounded and widely accepted concept takes a slightly different yet equally profound approach. This is known as pseudo-panspermia or molecular panspermia, and it focuses not on delivering life itself, but on delivering the absolute essential raw materials for life. Think of it not as receiving a fully grown tree, but as being gifted a bag of incredibly high-quality seeds, premium soil, and a detailed instruction manual. The core distinction here is crucial. Pseudo-panspermia suggests that space provided the probiotic ingredients, but the actual cooking, the transformation of those ingredients into a living cell, happened right here on Earth. This theory directly addresses one of the biggest puzzles of abiogenesis. How did Earth accumulate such a rich and diverse concentration of complex organic molecules so quickly? The early Earth was a violent and volatile place with a surface that was frequently sterilized by massive impacts. Creating these delicate molecules from scratch in such a chaotic environment would have been incredibly difficult. Pseudo-panspermia offers an elegant solution by proposing that our planet received a regular cosmic resupply mission. For hundreds of millions of years during the late heavy bombardment, asteroids and comets pummeled the young Earth. While these impacts were destructive on a global scale, they were also constructive, delivering vast quantities of two things absolutely vital for life: water and organic compounds. Comets, often described as dirty snowballs, are now understood to be more like icy dirt balls composed of water ice, frozen gases, and surprisingly complex organic dust. Analysis of comets like Halley and the spectacularly studied comet 67P/Churyumov-Gerasimen, CO by the Rosetta mission, has confirmed they contain a wealth of probiotic material, including the amino acid glycine and the key element phosphorus. Similarly, carbonaceous chondrite meteorites, as we've discussed, are veritable treasure chests of life's building blocks. They don't just carry a few random molecules, they deliver a pre-mixed cocktail of the very compounds that form the basis of all known biology. When these objects crashed into Earth, they didn't just leave craters, they delivered their precious cargo directly into the planet's early oceans and atmosphere. The contribution of water itself cannot be overstated. While some of Earth's water was undoubtedly outgassed from its interior through volcanic activity, the isotopic signatures of our ocean's hydrogen match more closely with that found in certain asteroids and comets. This suggests that a significant portion, if not the majority, of the water that fills our oceans and makes life possible was a gift from these celestial visitors. They literally delivered the solvent, the universal bath in which the chemistry of life could first begin to stir. The power of pseudo-panspermia is that it doesn't require us to believe in the incredible odds of a microbe surviving an interstellar journey. Instead, it relies on the well-documented and undeniable fact that the universe is a prolific factory for organic chemistry. We see these molecules in interstellar clouds around forming stars and in the asteroids and comets right here in our own solar system. The delivery of these materials to a young, receptive planet like Earth is not just plausible, it's an inevitable consequence of planetary formation. By providing a concentrated and constant influx of probiotic material, this process could have dramatically accelerated the path toward life, essentially priming Earth's pump and ensuring that the primordial soup was not just a thin broth, but a rich, nutrient-dense stew, perfectly prepared for the first sparks of life to ignite. The search for definitive proof is now moving from theoretical models into an era of direct, targeted investigation, driven by a new generation of missions and technologies designed to test the core tenets of the panspermia hypothesis. The most immediate and promising avenue lies not in the distant stars, but right next door with a series of ambitious sample return missions. NASA and the European Space Agency are jointly developing the Mars Sample Return Campaign, an incredibly complex endeavor that represents our best chance to answer the question of whether life ever existed on the Red Planet. The Perseverance rover is currently meticulously selecting and caching tubes of Martian rock and soil, carefully choosing samples from an ancient river delta environment that once held water and could have been ideal for preserving fossilized evidence of microbial life. These sealed containers will later be retrieved by another spacecraft, launched into orbit around Mars, and then captured by an orbiter for the journey back to Earth. Once here, they won't be opened in just any laboratory. They will be analyzed in a maximum biosafety level 4 facility, the same standard used for the most dangerous pathogens on Earth, to prevent any potential back contamination and to protect the pristine scientific value of the samples. Scientists will be able to subject these pieces of another world to the most powerful analytical instruments ever built, searching for subtle biosignatures like the precise ratio of carbon isotopes, the distribution of complex organic molecules, or even microscopic physical structures that could not have been formed by geology alone. Finding any convincing evidence of past Martian life would be monumental, but if that life shares a common biochemical ancestry with life on Earth using the same genetic code or handedness in its amino acids, it would provide the strongest evidence yet that lithopanspermia is not just possible, but that it actually happened, connecting our two worlds in a shared biological heritage. Beyond Mars, other celestial bodies are also coming into focus as repositories of cosmic history. Japan's Hayabusa 2 and NASA's OSIRIS-REx missions have already successfully collected material from asteroids Ryugu and Bennu, carbon-rich bodies that are essentially time capsules from the early solar system. The initial analysis of the Ryugu samples has been a stunning confirmation of the panspermia premise, revealing a rich array of amino acids and organic compounds, including uracil, a key building block of RNA. These missions demonstrate our growing capability to reach out and physically touch the raw ingredients of probiotic chemistry. The next logical step is a sample return mission to a comet nucleus, perhaps targeting a journey to a Jupiter family comet to bring back frozen material that has been preserved in the deep freeze of the outer solar system for billions of years. Analyzing the organic content of a comet could reveal the complexity of chemistry that occurs in the cold depths of space, potentially showing us the chain of events that leads from simple molecules to more complex, lifelike systems, all before they ever reach a planet. While we are reaching out to grab pieces of our solar system, our view of the galaxy is also becoming exponentially sharper. The next generation of space telescopes, like the recently launched James Webb Space Telescope and future concepts like the Habitable Worlds Observatory, are revolutionizing the field of astrobiology by allowing us to sniff the atmospheres of distant exoplanets. Using a technique called transmission spectroscopy, these powerful instruments can analyze the starlight that filters through a planet's atmosphere as it passes in front of its star, detecting the chemical fingerprints of specific gases. The goal is to find biosignatures, combinations of gases that are difficult to explain through geology alone, such as the simultaneous presence of oxygen and methane, which on Earth are constantly produced and consumed by living organisms. For panspermia, a crucial test will be to look for these biosignatures not just on one isolated exoplanet, but across multiple planets within the same compact system like TRAPPIST-1. If we were to detect the same specific, complex biosignature on several Earth-sized worlds orbiting the same star, it would be incredibly powerful, though not definitive, evidence for planetary cross-contamination. It would suggest a common biological source rather than multiple independent origins of life, painting a picture of a solar system widely inhabited by related species, a concept that would profoundly reshape our understanding of life's distribution. Finally, the entire endeavor rests on our ability to interpret what we find, and here too, technology is advancing at a breakneck pace. In laboratories around the world, scientists are developing instruments with sensitivities that border on the miraculous. New mass spectrometers can detect and identify individual molecules, allowing us to trace the precise chemical pathways of organic synthesis in meteorites. Crisp atomic-scale imaging with electron microscopes can now distinguish between a microscopic mineral formation and a potential microbial fossil with far greater confidence than was possible with the Martian meteorite LH84001. Perhaps most intriguingly, scientists are developing entirely new frameworks for detecting life that doesn't conform to our Earth-centric biases. They are creating chemical assays that could detect strange metabolisms, or instruments designed to find evidence of a hypothetical shadow biosphere that operates on a different biochemical principle than our own. This is crucial for panspermia, as it opens the door to discovering that life was not only transferred, but that multiple different types of life may have been delivered, some of which we have simply failed to recognize because we didn't know what to look for. The convergence of these technologies, the ability to retrieve pristine samples, to analyze atmospheres light years away, and to interrogate materials at the molecular level, means we are no longer simply speculating about our cosmic origins. We are building the tools to finally go out and find the evidence, to see if the seeds of life are indeed scattered everywhere, waiting for us to learn how to read the story they have been carrying for billions of years. This idea that we might all be descendants of ancient cosmic voyagers does far more than just answer a scientific question. It fundamentally reshapes our entire sense of identity and our place in the grand scheme of things. For millennia, human cultures have largely viewed our origins as a terrestrial event, a story contained within the boundaries of our own world, often guided by divine hands. The panspermia hypothesis, however, offers a new creation myth for the scientific age, one that is both humbling and empowering. It suggests that our lineage is not merely planetary but interstellar, that the very stuff of our being was forged in the hearts of distant stars and delivered across the void. This isn't about diminishing the miracle of life. It's about expanding its stage to a cosmic scale, transforming every living thing on Earth into a potential relative, all sharing a heritage that is literally written in the stars. It fosters a sense of profound connection not just to each other, but to the universe itself, redefining family in the most expansive way imaginable. This shift in perspective has long been a fertile ground for science fiction, which has explored the implications of panspermia with both wonder and caution. From the ancient alien engineers in 2001, a space odyssey who spur human evolution, to the terrifying biological imperative of the alien in Alien, and the more recent exploration in Prometheus that directly tackles the idea of humanity being a deliberate experiment by our engineers, the concept is a powerful narrative engine. It allows storytellers to explore themes of ancestry on a galactic scale, asking whether finding our creators would bring enlightenment or terror. It plays with the idea of a shared galactic biology, where creatures from different worlds might share a common genetic root, making the universe feel both more familiar and more strangely interconnected. Science fiction uses panspermia to ask the big questions. If we came from out there, does that mean we belong out there? Are we destined to return to the stars and continue the cycle, becoming the gardeners of life for other worlds ourselves? These stories provide a cultural playground where we can psychologically prepare for the monumental implications of such a discovery. Inevitably, this scientific theory also brushes against the domain of religion and spirituality. For some faith traditions, the idea that life began elsewhere could be seen as a challenge to divine creation narratives. Yet for many others, it presents no conflict at all. Indeed, it can be embraced as a revelation of the magnificent and intricate methods a creator might use, a universe-sized mechanism for sowing the seeds of life rather than a single, isolated miracle. It could be interpreted as the ultimate expression of a divine plan, one that operates on a scale beyond human comprehension. This fusion of science and spirit can lead to a deeply awe-inspiring cosmology, where the sacred is not confined to our planet but is woven into the very fabric of the cosmos. The universe itself becomes a living, generative entity, and our existence within it is part of a continuous, sacred process of creation and distribution. It invites a spirituality of vastness and connection, where looking through a telescope becomes a form of prayer, and understanding the chemistry of a meteorite becomes a way of reading a cosmic scripture. Ultimately, the most powerful impact of panspermia may be on our understanding of humanity's purpose and place. It shatters the notion of Earth as a lonely oasis in a sterile desert. Instead, it paints a picture of a galaxy that is potentially biologically active, where planets are not isolated islands but interconnected nodes in a vast living network. This moves us from a paradigm of isolation to one of relationship. Our responsibility changes too. If life can spread, then we are not just caretakers of a single world, but potential stewards of life itself. Our actions, our explorations, and our planetary protection protocols carry a new weight, as we must ensure we do not accidentally contaminate pristine worlds or carelessly extinguish our own, thus breaking a chain of life that may have stretched across billions of years and billions of miles. It suggests that our urge to explore space is not just a cultural or scientific impulse, but perhaps a deep biological calling, a desire to return to our cosmic roots and understand the family from which we came. In this view, every mission to Mars, every probe sent to a moon of Jupiter, is not just a voyage of discovery, but a pilgrimage. So where does all of this leave us? The panspermia hypothesis, once a fringe idea, has steadily gained scientific credibility, not as a proven fact, but as a profoundly compelling framework that elegantly addresses some of the most puzzling questions about life's origins. The evidence is multifaceted and increasingly difficult to ignore. We've discovered that the universe is a prolific factory for life's building blocks, with complex organic molecules like amino acids and nucleobases forming in the cold depths of interstellar space and arriving on Earth aboard meteorites. We've identified extremophiles right here on our own planet, tenacious organisms like tardigrades and Deinococcus radiodurans that can survive the incredible extremes of radiation, vacuum, and temperature that characterize an interplanetary journey. Laboratory and space station experiments have repeatedly confirmed that such a voyage is physically possible, provided life is shielded within the rocky interior of an asteroid or comet. And we now understand that our early solar system was a dynamic, interconnected environment where material was constantly being exchanged between planets, especially during the violent late heavy bombardment, creating a natural delivery system that could have ferried biological material from a potentially life-bearing ancient Mars to a freshly habitable Earth. Yet, for all its compelling logic, significant uncertainties remain. The hypothesis does not solve the ultimate mystery of abiogenesis. It simply relocates it to another time and place, leaving the initial spark of life from non-living matter as awe-inspiring as ever. The statistical improbability of a microbe surviving every single step of an interstellar journey, ejection, multi-million-year transit, and fiery atmospheric entry is still a formidable hurdle, and the question of whether life from one world could even be biochemically compatible with the environment of another remains an open and fascinating question. The scientific debate is healthy and ongoing, driving the need for more evidence, better models, and increasingly sophisticated missions. Panspermia is not a closed book, but an open invitation to investigate, to explore, and to keep questioning. Ultimately, the greatest power of this idea may not be in providing a definitive answer, but in how it radically expands our perspective on life itself. It challenges our Earth-centric view and suggests that biology might not be a rare, isolated phenomenon, but a fundamental, widespread process woven into the fabric of the cosmos. We are invited to see our solar system not as a collection of separate, lonely worlds, but as a potentially connected family, and our galaxy not as a silent void, but as a network of biological potential. This shift in thinking is a powerful catalyst for exploration. It gives profound purpose to our missions to Mars, to our study of asteroids and comets, and to our quest to analyze the atmospheres of distant exoplanets. We are no longer just looking for signs of habitability. We are looking for signs of relation, for clues that we are part of a much larger cosmic story of life. This journey of discovery belongs to all of us. The question of whether we are alone in the universe or whether we are all descendants of ancient cosmic voyagers is one of the most profound we can ever ask. We want to hear what you think. Does the idea of a universe seeded with life resonate with you? Do you believe our origins are purely terrestrial, or do you look up at the night sky and feel a deeper connection? Share your thoughts and your own theories in the comments below. Let's continue this incredible conversation together. And if you want to join us as we explore more of the universe's deepest mysteries, make sure to subscribe and hit the bell so you don't miss our next mind-expanding adventure.